All right, today we will revisit the canonical decomposition of a representation in the light of Fourier transform. So let us first recall the Fourier transform in the context of finite groups. So recall that for a finite abelian group. So first we shall recall the definition of Fourier transform of a function for abelian groups. So recall that for a finite abelian group G and a function in LG, its Fourier transform, which is denoted by f hat, is defined to be a function from G hat to C, which takes the value takes this value at a given point chi in G hat, or equivalently you can view f hat as the following tuple, the following k tuple of complex numbers. This is clear because since like we have already discussed that if a set X has an element, then Lx is the algebra. Lx is isomorphic to Cn as algebras over C. So every function can be regarded as a tuple once you have fixed an order of the elements in the beginning. So for a function f, its Fourier transform, either it can be defined as a function from G hat to C, or equivalently it can be defined as a tuple of complex numbers. Okay. So chi1 up to chi k are all irreducible characters of G. So as we have already discussed that when we want to extend the definition of Fourier transform to general groups, so then this tuple consideration of f hat as the tuple is going to be useful, not this one, because the main obstruction was since LG was the group algebra is non-commutative. So viewing f hat as a map, if you view f hat as a map in G hat as a map defined from G hat, then f is and then the f is being to f hat does not give an algebra does not give an isomorphism between the algebras LG and LG hat. So therefore, if we want to extend the theory or generalize the theory of Fourier transform, then this tuple consideration is going to be the crucial one, because that will help us, that will motivate us how to extend that in the how to extend the definition of the Fourier transform for any finite group. Okay. So if you send each f to the tuple, which is another which you can just regard as the Fourier transform of that if you wish, then the f is being mapped to this tuple that establishes an isomorphism between the group algebra LG and the direct sum of one-dimensional complex algebras of k copies. This is all what we have seen for abelian groups, finite abelian groups. When G is not necessarily abelian, then the Fourier transform of f is defined as this, which belongs to the direct sum of the endomorphism algebras, where Wi, rho I are, as usual, they denote all the inequivalent irreducible representations of G. The dimension of Wi is throughout denoted by Ni, and the character of this representation is denoted by the characteristics of this representation is denoted by chi I. Okay. So for any given LG, its Fourier transform is a member in the endomorphism, the direct sum of endomorphism algebras, and likewise the abelian case scenario. So here, yeah. So likewise, the abelian case scenario here also. So we get the following isomorphism between the group algebra LG and the direct sum of endomorphism algebras by sending each f to its Fourier transform. So it is just what we have seen for abelian case. This also holds in generality. So we have thus defined the notion of Fourier transform for general abelian, for general finite groups, extending that of the abelian situation. So yeah, one remark I would like to make here: you might, at this point, you might raise a mild objection that this general definition, when it is being specialized to the case G is abelian, then what we get does not exactly coincide with the definition of Fourier transform in the setup for abelian groups. Well, let me explain more. So what I am saying is, suppose you assume G to be abelian, so that each row I will be one dimensional, hence that can be identified with this character chi I. So therefore, in that case, this just simply turns out to be summation. It turns out to be the following: that the ith component is summation G over summation G belongs to G f G chi I G. So that is what it becomes in that case. But when we define the Fourier transform for abelian, in the setup of abelian groups, there we used to have chi I conjugate instead of chi I. So seeing this, you may not agree to accept this one. You may not agree to accept this one as the definition of Fourier transform for general groups, because apparently this differs with what it apparently differs with what we have earlier for abelian groups. Okay. So if you have that concern, then let me tell you, it is not any serious matter at all. Rather, it is just a matter of ordering. Well, let me explain. So let's observe the following that explains this concern, that suppose rho 1 to rho k are the inequivalent irreducible representations of G when G is assumed, when G is not necessarily abelian, then we just consider the dual representations of rho i's, and they will have the characters which are so the dual representation of rho I has the character chi I conjugate. Now, since each chi I is irreducible, so okay, let me again explain more. So each chi I is irreducible, therefore inner product of chi I with itself is 1. And then from there it is quite clear that inner product of chi I conjugate with itself is also 1. Therefore each chi I conjugate is irreducible. Okay, since chi I not equal to chi j, so is chi I conjugate not so is chi I conjugate and chi j conjugate. So therefore this means these are all irreducible characters, these are all different irreducible characters. Okay, and since they are different irreducible characters, then what does that mean? Then doesn't that mean that this is just a rearrangement of the chi i's? Because you have, for given G, you have only k many distinct irreducible characters. And here also you have a set of characters that where each of them is irreducible and they are distinct. So that means that these two sets must be same. So what happens that in view of that, you can say that is so what you can say is each rho I conjugate is also irreducible, and up to isomorphism this up to isomorphism, this is nothing but another ordering of rho 1 to rho k, because rho 1, let's say rho I conjugate, is actually isomorphic to some rho j or consequently at the level of characters, chi I is nothing but the conjugate of some chi j. So in view of this, we are convinced that when G is abelian, then the set of representations is nothing. Then the set of representations rho 1 to rho k is nothing but the set of the characters chi 1 bar, chi 1 bar, chi 2 bar, so on and so forth up to chi k bar. Recall that for an abelian case, each representation is irreducible representation is being identified with this character. So when G is abelian, this is nothing. This set is nothing but, so when is abelian, so each row I is identified with chi I. So this set is nothing but that set. And once you know that each row 1 to row k are actually so each of the row 1 to row k are actually the conjugation of some characters chi I. Then from that, now it is easy to see that when G is abelian, this will when G is abelian, then this will take the form of this up to an ordering. So, so now we are convinced that this indeed qualifies to be a general definition of Fourier transform in the context of finite groups. Let me just quickly again recall what I have done. We have first recalled the definition of Fourier transform in the set of a finite abelian groups. Then we generalize it for any finite abelian, any finite group. Then a possible exception was, then a possible a point of objection was that so the general definition when specialized, that does not exactly look like the previous one, but we then clarified that it is actually up to some ordering of the components. So now this is okay. Okay, so let's go ahead. So as I have just said, in fact, we have seen that sending F to its Fourier transform that establishes a isomorphism between these two algebras over C. So when this is an isomorphism between two algebras, so that isomorphism sends the center of one to the center of other. So yeah, so so F is being mapped to its Fourier transform for every F that maps the ZLG to the center of the direct sum of endomorphism algebras, and the center of the direct sum of endomorphism algebras is nothing but the direct sum of the centers of the direct sum of the centers of individual algebras. So thus so thus ZG is isomorphic to, so or more precisely, Fourier transform is an isomorphism between ZG to the direct sum of the centers. Now we observe that here a typical summand is ZNWI, which is nothing but, so what is the center of the endomorphism algebra of a vector space? So this is just all the scalar multiples of identity, right? So the scalar multiples of identity. Okay. So since each center is just a scalar, so since each center is the one-dimensional algebra, each center is just the one-dimensional algebra generated by identity. So from that we can say that we have an isomorphism between the direct sum of centers to the direct sum of C, which is given by so a typical element in the typical element here will look like this. That is some scalar multiple of the I1. I1 is the identity operator on W1. So in so we have already defined that II denotes the identity operator on WI. So a typical element here looks like this, and then we simply map it to alpha naught to alpha k. That gives an isomorphism between the direct sum and with the direct sum of centers to the direct sum one-dimensional complex algebras. So here we have an isomorphism, and Fourier transform establishes when Fourier transform is an isomorphism between this to that. So now it's legitimate to compose them. So once we compose these two, then we get the following isomorphism, that is sending each f to this tuple of complex numbers. Let me again explain how that came. So corresponding to each f, each f belonging to the center uh, is Fourier transform, which belongs here, is nothing but this. Okay, so each component is actually some scalar multiple of identity, and then once it's a scalar multiple of identity, we know how to compute that scalar. Namely, we will do by computing the trace. So the trace of a typical component here is summation fg chi ig, and so therefore the each operator operator, because every here each term is an operator on the corresponding vector space wi. So each operator is being mapped to the scalar, okay, which because yeah. So each operator here, since we know that it's a scalar multiple identity, so we map it to the corresponding scalar, and the scalar will be just 1 by the dimension times the trace. This is precisely what we have. In fact, this is not anything new. If you remember that z of ag is nothing but the set of our class functions. So therefore, we have already seen that if you start with a class function, then and for any irreducible representation, this is going to be a G-invariant map from G-invariant linear map on that vector space where the irreducible representation is being considered, and then that has to be a scalar multiple identity by Schur's lemma, and we can compute the scalar. So similar thing is also happening here. Okay, because we know that each f, for corresponding to each f in ZLG, whatever we are going to have here, they must be scalar multiples. Each term must be the scalar multiple of the respective identity operator. So we then just find out the scalar and map this tuple to the corresponding tuple of the scalars. And since this is the isomorphism of, this is the composition of the isomorphism, so therefore this has to be an isomorphism. Okay, now it is clear. Okay, so let's see that since this is an isomorphism, so if you consider the standard basis element here, for example, a typical typical element in the standard basis here is the following, that which has 1 at the ith component and 0 elsewhere. So that will have a pre-image. That will have a pre-image in ZLG. Now we wish to find what that pre-image is. It is easy to see that if you choose pi to be this, then this pi is going to be the pre-image of the ith standard vector, ith basis vector in the standard basis of CK. Just a direct verification, an easy verification. So thus these are nothing but the pre-images of the standard basis vectors, and hence since this is an algebra homomorphism, so these PIs will have these properties because their images will have the, for example, let me just give you some little bit more details. So what is the image of PI? This is in our usual terms. EI is the standard vector, so PI is being mapped to the standard vector EI, and PJ is mapped to the standard vector EJ. And now and here on CK, the algebra structure is coordinate wise multiplication. So EI and EJ, when they will take their product, if I equal to J, then it will be EI, and otherwise it will be 0. And summation of EI is here will be a vector that has all the component 1. So and the vector which has 1 in all the component, that is the identity element of this algebra. So therefore, what we get is the sum of the pre-images of the standard basis vector EIs is also the identity. So since the sum of EI is the identity element here, element of the algebra. So if we take and this is the algebra homomorphism. So if we just take the sum of their pre-images, then that is going to be the identity element in ZLG. What is the identity element in ZLG? This is just uh, don't confuse this E1 with the standard basis vector E1 in CK. Here E1 mean according to our usual notation. So 1 is the identity element in G. So E1 is the function that takes the value 1 at the point 1 at the point at the identity point of G and 0 elsewhere. So I mean, this should not be any confusion because this lies in ZLG. So this also has to lie in ZLG. So therefore, at least this cannot be the standard basis vector in CK. So here E1, at least you should not, in view of this, in view of the left side is just the sum of elements in ZLG. You should not confuse that this E1 is in CK. This E1 has to be in this C1 has to be in ZLG, and this C1 has to be the identity of ZLG, and identity element of ZLG is nothing but the function that takes the value 1 at identity and 0 elsewhere. Okay, so this is just statutory warning to you that you should not confuse that with the usual basis vector in CK. All right, so once we have these relations among CKs, now we observe the following. For any given complex representation of G, we consider the rho I hat. So since for any representation V rho sending F to F hat rho is a homomorphism from the group algebra to the endomorphism algebra of V. So from that, it follows. So yeah, from that it follows that this rho I hats, they have the relations. They have the following relations among themselves, because PIs have the relation among themselves since an algebra homomorphism that will simply be carried over inside endomorphism ring of V. So this is what we have. Okay. Now to finish that, we will to finish today's lecture. So denote the image of rho I hat is Vi. So now this just says that V is nothing but the sum of the vectors Vi, because for any small v, what the last identity shows is, so V is rho 1 hat rho applied on V plus rho 2 hat rho applied on V plus rho k hat rho applied on V. So therefore each V can be written as the sum of elements from VIs. So therefore this is the V is the sum of these subspaces. Now we will see that this sum is indeed a direct sum. How to see it's a direct sum? So it's very usual. We take elements from VIs. So remember that VI is the image of PI hat rho. So suppose that a sum like this, where V1, V2, Vk and V is 0. Now what we will do is, for any I, we will apply PI hat rho on both the sides. Use these relations. When you use this relation, you see that in that sum only the ith term will survive, and it will be exactly what it is, and everything else will be 0. So once you apply rho I hat here, you will end up the left hand side then becomes just this, and since the right hand side is 0, so that means this will be 0. That shows that each of the summand is 0, and therefore the sum is direct. Okay. Now, to finish, to complete today's lecture, observe that according to the definition, what is PI? According to the definition, what is this PI hat rho? So this is just right, because that's how we define. I mean that's how we define f hat rho for some function f, for any function f. So this is precisely this, and because this follows from the definition of PI. So in view of the definition of PI, let me just show you once again. Since PI is this, so PI hat has to be this. And now I think you can remember you can remember that this is what the operator we considered when we discussed the canonical decomposition of a representation. So therefore, the VI defined here. So for each I, the VI defined here is just the image of PI hat rho. Since PI hat rho is the that PI what we have considered in the canonical, when we studied canonical decomposition. So the image of this is same as image of that. That is each VI here is nothing but each VI here coincides, or each VI here is nothing but the VI there, and therefore now it is quite clear to us that this decomposition, what we get here is nothing but the our well-known canonical decomposition of the representation rho. So this is another way of obtaining the canonical decomposition of a representation. And this way, as we have seen, that this way is this approach is based on the Fourier transform of a group. Okay, so with that I will stop. So yeah, no, so I just the last sentence that I said has as an unintentional mistake. So what I wanted to say is that's how we get the canonical decomposition. So this way of obtaining the canonical decomposition, this approach is based on the Fourier transform on finite groups. So earlier I said Fourier transform of groups. That's not correct. Fourier transform on finite groups. That's the correct thing. Okay, with that I will stop.